got what we call Riemann's sums. This kind of collects everything we've been doing in section 5 together. This pulls those indefinite integrals into play, and it pulls the limit definition of derivatives in there. And so let's just take a look at this. Here's our definition, and so let's get that out. Closed interval, okay, so we've got a function defined on a closed interval. Delta, and it really should, it'd be like delta x in there, but delta is a partition of the interval, and A is the beginning of the interval, B is the end of the interval, and this is just saying that we've got input values between A and B. That's all it's saying. A sub 0 is the endpoint on that side, and x sub n is the endpoint on that side, and then it just says we have lots of input values in between. Delta x sub I is the ith subinterval, meaning that it is, if I want what is the third rectangle, okay, then I would use the delta x sub 3 in order to determine what that third rectangle's base is. Then the sum, okay, and this is what the whole section 5.2 is about. The sum, as I ranges from 1 to n. Now here is that delta x sub I. When you were listening to that video from section 5.2, that piece, now remember, we're summing up the areas of rectangles. This piece right here, and I mentioned it just a few minutes ago, represents what of the rectangle? The base, yes, the base. So this is the base of the rectangle. What does this represent then? This would be the height. Remember, the height of the rectangle is dependent upon the point, or the distance from the horizontal, the input axis, up to the function, and so this would represent then that height of that rectangle. Okay, where c sub I is somewhere between x sub I minus 1 and x sub I. It's called the Riemann sum. Okay, basically all it's saying is that we're going to take some curve, and we're going to set up an interval, and we're going to set up rectangles, and somewhere in here is a base that we're going to be using for our rectangle, and so maybe that's the base of our rectangle, and the height of that rectangle is going to be dependent. Whoops, kind of messed that up a little bit. Let's go back and draw it. We'll draw it this way using that left end point. Okay, so it's dependent upon, what's the height is dependent upon f of x sub, or f of c sub I. So that's all that we're really saying, is defining what we mean by Riemann sums. Okay, let's go on. A definite integral. Here we go again, closed interval, a to b, and the definite integral, again, this was established back in 5.2, so hopefully you all listen to it carefully, is the limit of the summation of, let's start this way, it's the summation of all those rectangles that we describe or define under the curve, and we take, this says delta x to 0. Now, the other way of saying that is that n goes to infinity. Are those saying the same thing? If n's the number of rectangles and n goes to infinity, what's the width of the base? What's the base of those rectangles? Getting smaller and smaller until you have almost what kind of a base? No, which would be 0. Okay, and that's what this is saying. Delta x is going to 0. So that means the width of the rectangle is shrinking to 0, which is the same thing as saying that n goes to infinity. Okay. Again, you've got the base and the height defined there. It says if the function is closed and this limit exists, okay, then the function is integratable on the interval, and the limit is denoted by, this is the bridge. This is the bridge between section 5.1 and section 5.2. In section 5.1, whoops, let's go back to our notes here. In section 5.1, we looked at an indefinite integral. And we talked about then how we were looking at area under the curve. How do those indefinite integrals, how does all of those rules that we looked at, how does the substitution rule for integration play in here? It means that we're going to have to find the antiderivative, use all those rules that we know. But now notice, you've got this A and you've got this B. What do A and B represent? Yeah, right here. This is the A, and this is the B. So we're saying that we're going to find the area under the curve between or on the closed interval from A to B. We're going to, in order to do that, we're going to have to find the antiderivative. Now, we haven't told you yet how these values A to B play in. Right now, I'm just saying we have to find the antiderivative. Finding the antiderivative and then doing something with this A to B is the same thing as doing this whole limit process back here. Again, this is to integrals as the limit definition for derivatives was to that section that came after that. What was it, 5.3 or 5.2, where we were thrilled that we started using those rules. Okay, so section 5.2 is really just looking at a lot of these definitions. A lot of this definition without actually doing any work. I mean, what can I say? Without actually completing the problems. So this is still just going off of that basic definition that we just talked about. Okay, so write the limit. Write this limit as a definite integral on the interval 0 to 4 where c sub I is any point in the ith interval. Okay, so all we're looking for is how do I translate this into something like that? Okay, that's all we're looking at. Now, let me go back on my notes here. We have been using, let me see where we first look at this. We have been using delta x as we see it here. Notice that in this definition, there's some lines around the delta. It doesn't really say delta x, it just says delta, which is a little odd, but let me explain what this is. We have been looking in the section 5.2, it's been described as having rectangles of the same width all the way across. You don't always have to have rectangles of the same width. You can have different width rectangles. It makes it a little more difficult, though. When things are uniform, then you got so many of the same thing, and it makes it easy to work. So what we have here is called a norm particle. And so this thing, let me move this out of the way for now. This thing here, and you see that, that's known as a norm partition. Not particle, but partition. And what we do here, we're going to treat it, we're not going to worry about it. So when you get this in the reading in the book, we're not going to worry about norm partitions. We're going to assume that everything is equal partitions. Okay? Makes it a little easier. Those who are in Math 70, you'll pick this up in greater detail. But I just want to explain what this refers to. It means that not every rectangle has the same width to it. But we're going to treat it as if it does. So we're going to use delta x, and if you remember back in section 5.2, how do we determine the width of the rectangles? Well, for this one, if I know I'm going from 0 to 4, and if I want, let's say, 4 rectangles, what's the width of each one? So I'd have 0 to 4. Actually, I'm going to, since it is subtraction, it is not commutative, so it's going to have to be 4 minus 0 divided by 4. And, of course, that would be 1. So the width of each one is 1. What if I want to have 8 rectangles? What's the width of each one then? 1/2. Okay, I got 4 units there. I want each one to be half a unit, so how many halves do I have in 4? Well, I have 8 halves, and so forth and so on. So we're going to continue to use that delta x is b minus a divided by n. I just wanted to explain what that double line symbol is. Okay, so the problem says to write this as a definite integral. Now again, if I'm on the interval from 0 to 4, where does this information go? Yeah, called the lower and upper boundaries. Okay, so 0 to 4. And now what I need to do is I need to change this whole thing of the summation of 6c sub I 4 minus c sub I squared delta x sub I into some kind of an integrand followed by what? You always have to have the differential x. Yeah. Okay, it's all followed by dx. So the question is, what goes in here? What goes in there? I'll give you a moment to think about that. You might want to go back to this statement. Notice that you've got f of c sub I in here, but you have f of x in here. Why x? Well, if you're going to use differential x, it's got to match. So this has to be in terms of x. What would the integrand be? Anyone want to give it a shot at this? What do you think it might be? Let's start with this. Inside, the integrand here is f of c sub I, so that's what? Just what you see? 6c sub I times the quantity 4 minus c sub I quantity squared. And what we want is not f of c sub I, we want what? F of x. What do you do when you have a replacement for the input variable? Yeah, it's the same thing we always do, right? Everywhere you see that input variable, you're going to substitute the new value for. So this would be 6x times 4 minus x quantity squared. Okay, we've identified, we can see that up here, this is f of c sub I. Again, going back to here, f of c sub I is this summation expression, and we need to translate that into f of x. If we can identify what f of c sub I is, and you want that to be f of x instead, it's the same thing we've always done since Algebra 1. Wherever you see an input variable and you have another expression for it, you write that expression in there. Okay, so that's it. That's all we're doing with that problem, is just writing it as a definite integral. Now, could you solve this definite integral? Now, if it was indefinite, don't worry about the 0 and 4, but can you find the antiderivative of this? Now remember, this section comes before section 5.5. So if you're in section 5.2 and 5.3 and 5.4, you're not supposed to know anything about integration by substitution. So if you were going to find the antiderivative, what would you need to do for this? Lindsay? Yeah, expand it. Then you'd have, let's see, that's going to be a cubic, and so then you'd have maybe 4 terms, and you could break it into 4 different integrals, indefinite integrals, and find them that way. Okay, well, let's go on. Continuity implies integratability. Now, just by that title, what's that tell us? Yeah, just go ahead. What's it tell us, Jenna? Yeah, If it's continuous, it implies that it's integratable. That's what it says. Okay. If the function is continuous on the closed interval, then the function is integratable on the